Now let's start today's class. Okay. Now we're gonna change our topic quite drastically. So now our focus is from computation to communication. That's what. Therefore, it's of course it's in the computation. It's usually one party is involved, but from now several parties get involved. That's why the communication is important. And in such a situation, we usually use the term protocol instead of algorithms, protocols instead of algorithms. So the idea is the same. The idea is the same. Some procedure of computation or communication, but we usually use the term protocols rather than algorithms. So probably I'm going to use this protocol quite often from now. Okay. So I have a big change from today. And chapter 4 is protecting and hiding information. If you talk about communication, then that this protection and hiding of information is always the most important topics. Yeah. For example, the very recently, you know the news which happened, which came from the United States. They have their national security agency, I don't know, NSA, kind of important agency, government agency, but there was a big incident over there, kind of scandal over there. So it's always this topic is important when you talk about communication. Okay, so let's quickly go to the first example. Example 1, this is testing. Testing and matching. Of course, without leaking information. So this is important. It's important. Okay. So let's assume the following situation. We have n men and n women. And each woman, each girl has a preference in her mind. Okay, so So, for example, I don't know, this Alice likes Bob, and maybe Betty like Charlie, and so on and so forth. So once again, you have n women, n men, and n women, and each woman has her preference in her mind. Of course, in her mind. It's not open. It's not open. Okay? Do you understand the situation? It's just quite a natural situation. Now, so now, n women want to know whether if their selections are peaceful. Peaceful means no collision. No collision. So, for example, if Alice likes Bob, and if some other woman likes Bob also, then no, here is a collision. So this is not peaceful. This is not peaceful. Okay. So more formally speaking, they want to check if preferences they want to check if their preferences are a matching or not. Matching is what? Okay, matching is just a one-to-one correspondence. One-to-one, no collision at all. Okay? So we have n men and n women. So matching just means one-to-one correspondence. One-to-one matching. There are no collision like this. Okay. But so this is important. We have one important restriction, we have one important assumption that we have to do this without any leak of information other than whether it is a matching or not. So whether it is a matching or not, this is what we want to check. What we want to check. So of course, we'd like to know if it is matching or not. But we don't want to leak any other information. Okay. So for example, what about just voting, just anonymous voting? For example, anonymous voting. Anonymous voting means just vote, just vote. You put your preference on the paper and just vote. Okay. For example, it's, if Alice likes Bob, then Alice writes the name of Bob. Just write Bob. Just on a piece of paper, then just vote. Just vote. This is anonymous voting. This is very standard strategy, standard process. But this is not good. Not good. This is not good. Why? Why? Because okay. Anonymous voting is good. Anonymous voting is good if it is matching. Okay, if it is a matching, then you open the vote. Then you can find all the names exactly once. Okay? That means it's a matching. So no information is leaked. Of course, no other information is leaked. So if it is a matching, then anonymous voting works, does work. But if it is not a matching, then several information leaks. Very important information leaks. For example, Bob gets 3 votes. 3 votes. And Alan gets no votes, and so on and so forth. Okay, this is a very important information leaking. Okay, it's you don't know, you don't this is quite, in the real world, this is quite important. For Bob, it's okay, but for Alan, it's sort of shame. So just does not want, this kind of situation. Okay? Now you understand the situation, right? Good. So I'll show you one good protocol. Maybe there may be other even better protocols, but the following protocol is very simple and cute. It's very simple and cute. Okay. Suppose we have 5 guys. Alan, Bob, and maybe we have 5 guys. Then we prepare just five glasses, just glass, water glasses. And also, we have 5 ladies, Alice, Betty, 5 ladies. And for each girl, we prepare 5 small pieces of papers. 5 small pieces of papers. Oh, this is just, this is a small paper. So, yeah. And importantly, Alice, check. Okay. Check. Exactly one of 5 papers. Check. Okay. Now voting process. Alice likes sport. Okay. Alice likes sport. Then Alice should put this. Oh, I'm sorry. Very important. You have to fold small papers. Fold. So as this mark is not visible. You can't see which paper has a mark. All paper you fold all the paper into small pieces. Fold. Okay? So now you can't see this mark. Then Alice should put this marked paper into Bob's bin, Bob's glass. Okay? And of course, no marked paper to all other guys. So just like you have five pieces of papers, and you have to remember which one has a mark. This is sort of important. Okay? You have to remember, but that is not visible. But of course, you have to remember the 1, 2, 3, 4, 5. Oh, this is my important paper. Okay? Now 5 glasses. You have 5 glasses. Okay. Oh, this is my not favorite guy. Oh, this is my guy. You put the marked paper, and this guy's done. Okay. Now, after the voting, this is number 1, number 2, number 3. Now we have open. We're going to open the votes. Okay. There are 5 pieces in each bin. After the voting, each bin has 5 pieces of the papers, right? Because each lady puts 1 paper into each bin. So each bin has 5 pieces of papers. Now let's open the vote. This is a little bit tricky. Okay. We first open this vote. No mark. Okay. Now we open second vote. No mark. Okay. Now we open the third paper, third vote, mark. Now we stop here. We leave the remaining two papers not opened. Okay? We stop here. Then go to the next glass. With the same thing. Okay? No mark. Oh, mark. Then again, we go to this. if you can go through the all 5 glasses, then what does it mean? It means matching. Okay? We can find one marked paper, one marked paper, one marked paper, one marked paper, and one marked paper. That is matching. Right? Otherwise, for example, when you go to the second class, no mark, no mark, no mark, no mark, no mark. There's no marked paper in it. Then of course we can stop here, because that is not matching. Some guy, oh, I'm sorry. I also forget one important process. Shuffle. We collect 5 glasses on a table, shuffle, shuffle, shuffle. I'm sorry, this is important. Important. Shuffle, 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 you know, to make, you know, so now you don't know which glass comes from which guy. Okay? Shuffle, 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 shuffle. Then do this. Now second glass has no votes, has no marked paper. That is evidence. That's a certificate that is not matching. And there is no information leak. There is no information leak, right? Because what is the definition of matching? Okay. If it is not a matching, it is not a matching if and only if there is one guy who does not have any vote. That's the definition of matching. So, even if you can find one empty bin that does not leak any information other than that is not matching. Right? For example, no information like, as before, Bob gets 3 votes. This is important information leak, but now we don't have any such information leak. Once again, very importantly, when you open the vote, if you find one marked paper, then you have to stop there. Stop there. Because if you continue opening the vote, then maybe the next one has also mark. And this is a very important information leak, because I don't know if this, which guy's bin is this. But even so, some guy has more than 2 votes. That is more, kind of information leak. Yeah. So you have to stop here. If you find one marked paper, then you have to stop here. Stop there. Okay? Maybe you can come up with some other better protocol about this game. Yeah. But this is a very simple and cute protocol. Okay? So now you can understand that what I mean. What I mean by not leaking information. Okay. Now let's go to the more serious example. Example 2. The idea is the same. Our goal is the same. Proving something without leaking information. The previous example is the same. Basically the same. Because you want to prove that the current matching is just 1-to-1. Okay? So the idea is the same, but now the problem is more serious. Okay. Now the situation is this. Just think of this situation. We have a conversation between big brother and the young brother. Okay? Big brother may be Bob. And younger brother, Charlie? I don't know. Okay. Okay. Now Charlie. He's something like elementary school student, maybe third grade. So he knows multiplication. Okay, but he doesn't know any sophisticated mathematics. Now Charlie asks to Bob. Oh, he's maybe a high school student. Or he has a lot of mathematics. Okay. Now Charlie asks. Do you know square root of 121? Okay? Charlie is an elementary school student. He knows the definition of square root, but he can't calculate it. Okay? Of course, yes. It is 11. Now, It is correct. It is correct. Because Charlie can do multiplication. Okay? So just, he multiplied 11 by 11, then that is 121. Okay? So he says, it's correct. It's correct. This is a very important point. Square rooting is not so easy. But checking is not difficult. Pretty easy. Just multiplying 11 and 11. Then it's 121. Then, square root of 121 is exactly 11. Okay? Now, Charlie asks, do you know square root of 225? Okay. Now, Bob, now he's fooling me. Wow, it's endless. Now, he's thinking, wow, he's fooling me. Okay. Okay. Now Bob is thinking that, oh, now he's fooling me. Oh, he's asking his homework to me. Or maybe not. Okay. So what he's thinking is it possible? Is it possible for me, to convince him that I do know the answer, but I don't want to reveal. I don't want to reveal the answer itself. What is the answer? Answer is a square root, the number. I do know 11. I do know, what is that? Is that 15? I don't know. Okay, maybe it's 15. I do know the square root of 225 is 15, but I don't want to reveal the number of 15. Is it possible? This is our goal. That is exactly proving something without leaking information. Okay, now a problem. More formally, okay. What is the formal description of the problem? We are given two integers, x and n. And the question is x a quadratic residue? Meaning, is the number y such that x is equal to y squared mod n? Mod n. This mod n is important. Mod n is important. So example, x is equal to 3, then the answer is yes. Because, yes. If x is 3, then answer is and n is 11, then the answer is enough. Answer is yes, because 5 squared is 3 mod 11. That means 3, x is equal to some number squared mod 10. Okay? In this case, the answer is yes. Importantly, This problem is known to be very hard. This problem is known to be very hard, meaning we don't have any sufficient algorithms other than just exhaustive search. Exhaustive search meaning just check. Just check. For this problem, just exhaustive search means 1 by 1 is equal to 1, 2 by 2 is equal to 4, 3 by 3 is equal to 9, and 4 by 4 are. Over 4 is 16, mod 11 is 5, right? Yes. And and 5 by 5 is 3. Okay? So we are done. So the exhaustive search is just go through from 1 by 1 to n by n. That is just exhaustive search. Okay? So we don't have any sufficient algorithm other than this kind of exhaustive search. That's very important. Okay. That's why this mode, the mode n is very important. Because if you don't have this mod n, then the problem is easy. Square root of 225 is pretty easy because you can do binary search, right? You can do binary search. Just try to I don't know, something like 100. It's too much. Then 50, too much. 25, too much. Maybe 13. Too small, then something like that. You can do binary search. Okay, so that is if you don't have a modern part, then it is not so difficult. It's easy. But if you do have this modern, finite computation, then this is a very difficult problem. It's known to be a difficult. Okay. Now I'll show you surprising protocol. It's exactly which achieves this goal. So here's our protocol. Protocol means just a sequence of communication between Alice and Bob. Sequence of communication between Alice and Bob. And importantly, we assume that exactly as before, Alice has a high computation power, so unlimited power. We assume unlimited. Unlimited power. But Bob has a small computation power, so polynomial time computation. Well, meaning, it's not so important. It's not so important to make exact division of polynomial type computation. Just you can think that Bob cannot obtain a square root of a number. Impossible. Just like a Charlie. His computation power is limited. He cannot square rooting He cannot square root some number, but he can do multiplication. He can check, like this. He can check. Okay? Now, our requirement. So we want to design the following protocol requirement. We have 3 requirements. The requirement number 1, okay, if okay. The first requirement is pretty natural. If a given instance is a yes instance, that means if X is a quadratic residue, then, by following this protocol, there is an Alice action. There is an Alice's action that should follow that protocol, by which Bob accepts the input with probability 1. Always accept. So supposing that you are following the protocol, I'll show you the protocol in a moment. Protocol is just exchange of numbers. Just exchange of numbers and some small computation. By following that computation, then there's Alice's strategy, which makes the Bob go to acceptance with high probability. Okay? Number 1. Number 2, otherwise. The answer is no. For otherwise, namely, if the answer is no, if X is not a quadratic residue, then so something like 97. Okay, if the number is 97, that is not a quadratic residue, then for any Alice's action, Bob rejects the input with high probability. The third requirement is, of course, is hiding information. In the yes case, Alice does not give any information about the answer to Bob. Okay. So now 1 and 3, Alice. Alice can convince Bob that she knows the answer without information. Number 2 means if cannot, if Alice does not know the answer, she cannot cheat Bob. This is, of course, very important. This is considered very important because if only our requirements are only 1, 3, then there's some trivial protocol. Just Bob always accept. That is a definition. That is following the definition. So number 2 is very important. If Alice does not know the answer, then she cannot make Bob to go to acceptance. And of course, if the answer is no, then of course Alice does not know the answer. Okay? So I'll show you the following protocol. It satisfies these conditions. It's really amazing. No information leaking, but still Alice can convince that she knows the square root of x. Now, Alice and Bob. The protocol is very simple. Integer z, bit b. Very simple protocol. Very simple protocol. So just the protocol includes one integer from Alice to Bob, one bit from Bob to Alice, and another integer from Alice to Bob. That's it. That's it. Then this is a 3-round protocol. Just 3-round protocol. And this is a condition. This is a small computation. This is just a small computation in the Bob side. The Bob side, just deciding if he accepts the input or not. Just a small computation. Here. The protocol. So this protocol satisfies the requirements, all requirements. It's really amazing. I'll show you. Okay. Okay. The case 1. Requirement number 1. Requirement number 1. Suppose that the answer is yes. That means x is a quadratic residue. X is a quadratic residue. Then Alice is strategy. Now Alice's strategy is here. 1. She generates a random number. Oh, random number. Number 2. Just she decides the number z, number z. That is equal to r squared mod n. So she prepares the number z and send it to Bob. Send it to Bob. Now, Bob, answers back with 1 bit. Okay, then she prepares integer w1 or w2 just by following this simple rule. Simple rule. If Bob sends b is equal to 0, then her w1 is just r mod n. w2 is y r mod n. This y is what? Oh, I'm sorry. Of course, Alice knows the answer because Alice has unlimited computation power. She knows the answer. She knows the answer y. She knows the answer y. So W2 is just y multiplied by r. Y times r. Bob's strategy just Bob's strategy is almost nothing. Bob's strategy is also almost nothing. Just select this bit B at random, 0 or 1 at random. So this is requirement number 1. So requirement number 1 says, if the answer is yes, there is Alice's strategy. There is Alice's strategy that Bob goes to acceptance. Bob goes to acceptance. Let's check. Let's check. If okay. If B is equal to 0, if B is equal to 0, then W1 is equal to R, and Z is equal to, of course, Z is equal to R square. R square. So, of course, Z is equal to W1 square Bob. Bob accepts. Right? This is just a condition. Okay? That is equal to R square. That is R square. And W1 is equal to R. Okay? So obviously it satisfies this condition. So Bob accepts. Right? Okay? Good. If B is equal to 1, then that is the same as before, R square, and W2 is YR. YR. Okay? YR. Then, you know, what Bob checks is XZ. XZ is equal to X is equal to Y square. X is Y square. And that is R square. And W2 is YR, so that is W2 squared. Bob accepts. Bob accepts. So in any case, whether or not B is equal to 1 or 0, Bob accepts. Okay? Number 1 is satisfied. Okay. Now requirement number 2. Requirement number 2. Okay. Okay. That's fine. That's fine. Okay. What is the requirement number 2? What's the requirement number 2? If you follow this protocol, then there is no Alice's strategy. No Alice's strategy. no Alice's strategy which makes Bob go to acceptance. It is impossible for Alice to make Bob accept the input. Okay? Let's check. Okay. Alice's strategy is just decide those three numbers, Z, W1, and W2. Okay. So no numbers, no selection for those three numbers. It is impossible to make Bob accept input. Okay. So we check for any numbers, for any those numbers, Bob rejects. So case 1 is that Z, the first number. The first number is not a quadratic residue. Not a quadratic residue. Okay? Then, by following the protocol, with the probability 1/2, B is equal to 0. 0 is coming back from Bob as B. Okay? Then Bob rejects because why? That is not a quadratic residue. That is not a quadratic residue. So for any W1, that cannot be equal to a W1 squared because we assume that that is not quadratic residue. There's no number. For W1 that makes Bob go to acceptance. Right? Now, second case. Now, that is a quadratic residue. That means that is one squared moten. Now, with probability 1/2, B equal to 1 comes back from Bob. Then if Alice selects Z as not a quadratic residue, then she fails. She fails. Now, if she selects Z as a quadratic residue, that means Z is equal to Y squared. Then, again, she fails. Why? Now, with the probability 1/2, B is equal to 1 comes back. Then Bob rejects. Why? Let's check. Now, suppose for contradiction, she accepts, he accepts. Then here, he accepts. That means xz is equal to w2 squared. That means in this case, z is equal to y squared. So xy squared is w2 squared. Okay? Then w2 is of course square root of xy squared. That means x is y squared or square root x exists. I know this is just kind of if you think of factorization, elementary factorization, this is obvious. Contradiction. Why? Because x is not a quadratic residue. Recommend number 2. Just remember, otherwise, if the answer is no, that is x is not a quadratic residue, then this is a contradiction. Requirement 2 is also satisfied. Amazing. Now, most importantly, requirement 3. Now, I'm going to use a red pen. Also okay. Why? Requirement 3 says, if the answer is yes, that means x is a quadratic residue, then Iris does not give any information about the answer. Let's check. Okay? Now, what is Iris' strategy? Generate a random number r, and z is r squared. So z obviously includes no information about the square root of x. That is just a random number, right? No information about the answer. Okay. What is w1? W1 is also a random number. No information about x at all, right? This might be a little bit subtle. Y is answer. But y is answer, but multiplied by a random number, secret random number. Okay? This is the answer, but if it's multiplied by a secret random number, then for Bob, it looks just a random number. Or just, you have some number. But if it's multiplied by a random number, then the result looks random number. Okay? Why this R is the secret? Okay. Again, this is a little bit subtle. Because at the beginning, Alice sends R squared to Bob. Okay? So if Bob has good computation power, then he can figure that what number this R is. But we are now assuming that it is impossible. Bob cannot make a square rooting. Cannot make a square rooting of a given number. So this R is still secret. Okay, this R is secret for Bob. Bob does not know this random number. So that means this W2 just looks a random number for Bob. So no information leaks. If maybe you might be puzzled, then just after coming back to your apartment, you just look back, just follow this protocol once again very, very carefully. I'm not cheating. No, I'm not cheating. Exactly correct. Exactly correct. Okay. So once again, I can convince Bob that she knows the answer without leaking any information. But if she does not know the answer, then she cannot cheat him. Okay, some people say this is only 1/2, probability 1/2. If the answer is no, then the Bob rejects only with probability 1/2. So this is not high. You might say this is not high probability. But of course, you can repeat the same procedure many times, maybe 10 times. Then, of course, the probability, gets larger, something like 1/2 to the. I'm sorry. The rejecting, if you repeat this procedure 10 times, and reject, if there's any sequence, so it's 10 times. Repeat 10 times. Accept if all accepts. Reject otherwise. Then again, if the answer is yes, then the Bob accepts with probability 1, and if the answer is no, then Bob rejects what? 1 minus 1/2 to the 10th. Okay? So it's the almost always reject. Almost always reject. Good. We are almost done. But an important remark. Okay, here's an important remark. Why we need this B? Why we need this B? Because, it's natural. Some of you are thinking that B is equal to 0 is useless. Why? It's nothing. It's nothing to do with the answer. It's nothing to do with the input. Not only the answer, but the input itself. Only random number. Okay? Nothing to do with the input. Why do we need this B equals 0? Of course, this is somehow related to the input because it involves Y. Okay, it involves Y. So B equals to 1 somehow related to the input. But B equals 0, nothing to do with the input. Why we need B is equal to 0? This is important. This is really, really important. Okay, suppose that Alice knows that Bob always sends back b equal to 1. Then Alice can do this trick. Okay? Just remember, Alice must send this integer z before b. Before b. Okay, not after b. Before b. This is important. Okay? Alice has to send this z before b. But if Alice knows that Bob always sends b is equal to 1, then Alice, includes some trick into this number z. Now, z is not r squared, but r squared divided by x. Then, look at this. X times z is equal to just exact r squared. So Bob accepts. So that means Alice can cheat Bob. But of course, if b is equal to 0 comes, then this fails. You can check it by yourself. Pretty easy. Pretty easy. This fails means Bob rejects. Bob rejects. Okay. So we are done. This protocol is really amazing. That is called zero knowledge proof. And this idea came out around, I don't remember, 1990s. And this became a big, big sensation. Okay. And this is just only for one problem, but you can use this kind of amazing protocol for many, many different problems. Yeah. It's really, really amazing. Just imagine you can prove something without revealing the answer itself. But still, you can prove that you know the answer. Okay, so really, really amazing. Good. So okay, we are done today, and the next week, maybe it's I will be stay on the same line. We will be stay on the same line. That means it's kind of our main topic is communication. Communication. Okay, so see you next week.